All right, so let me start by talking about ODP 202. That's the next ODP. It opened up about 2 hours ago. It's due tomorrow morning at 8. Let me run through the details of that. And this is a piece of something you'll get to use in programming assignment 1. So it's a chunk of that project that's coming up. So I'll talk about ODP 202. I'll talk a little more about structure statements. And then I want to have people go to the board and work in groups doing some of these linked list operations that we started to talk about yesterday. And then we're going to come back and we're going to talk about what's called an abstract data type. It's going to be a key concept that we'll come back to again and again throughout this course, the notion of an abstract data type. And then time permitting, we'll start on PA1. Otherwise, we'll start talking about PA1 tomorrow in detail. So let's take a look at ODP 202, which I should have logged in ahead of time, but I didn't. So ODP 202, we're basically making an array of structures and making one function to manipulate it. Okay, so your structure should be called node, lowercase, and it should describe 3 fields, data, next, and valid. Each of those is an integer. So, so syntax-wise, right, this looks something like this. Struct node. And then data next valid. All right, there's half your ODP. So keyword struct node is the name of the structure we're defining. Curly brackets at the beginning and end. And then just a list of the variables that comprise your structure. In this case, 3 integers named data, next, and valid. Closing curly bracket has to be followed by a semicolon. Okay, you'll get all kinds of weird errors if you don't have that closing semicolon. And there's a note in here, these have to be specified in this order. If you put them in a different order, different things will happen. Things that result in like a 0 out of 10 instead of a 10 out of 10. So the order is absolutely critical when you define a structure. Okay, the reason being that you're going to take code, you're going to develop it to work with this structure, and you're going to link that in with my test bed. Well, my test bed defines a structure to have these fields in this order. And if your fields are in a different order, the poor system has no way of knowing that what you're calling data, I'm calling next. And when I try to access the value of next, I'm going to be accessing your data, and it's just not going to work. So the order is absolutely critical. Okay, so you're writing one function. Its name is init, lowercase init. A prototype looks like this. It returns nothing, so the return type is specified as void. Okay, and void is not a type of variable. It's a keyword which says there is nothing being returned from this function. So void init, and then it takes one argument, which is a struct node star. So if you have a variable type star, that's the way that we describe an array of that variable type. So the argument to init is an array of struct nodes. So if I was writing a main program to work with this, right, I could declare it integer or void or whatever, but I'm not going to pass anything to main or take anything back. So just void main, struct node data bracket 100. Okay, this declares data to be an array of 100 struct nodes. And since I'm declaring a function named init which accepts a pointer to a struct node, that expects an array of struct nodes. So I could say init parentheses data. That's an example of passing an array of struct nodes to the init function. And my init function itself is declared like the prototype. And it doesn't matter what you call the argument, you can call it whatever you want. I'll just call it x. And this function is supposed to do something to the elements of this array. Okay, so what does init do? It does the following things. It sets element 0 to have the following values. Valid equals 1, data equals 42, next equals -1. And then it runs a loop to set elements 1 through 99 with the following values. Valid equals 0, data equals 999, next equals negative 99,999. There's no particular reason for doing this other than I'm asking you to do it. So what would the first line of init look like if we wanted to set element 0 to have these values? It's pretty straightforward. So what's our first thing? Valid should be 1. X bracket 0 dot valid equals 1. That takes care of that first requirement. So X is the array, right? X bracket 0 asks for the first element of that array. Dot valid asks for the field named valid. And this sets it equal to 1. We also want to set the data field of that element to 42. So X bracket 0 dot data equals 42. And we want to set the next field equal to -1. X bracket 0 dot next equals -1. Okay, and then we need a loop. So in our loop, we want to set valid equal to 0. Data equal to 999. And next equal to negative 99999 for I equals 1 to 99. So you got to actually write that loop. But other than that, this is your init function for ODP 40202. But same idea, x bracket I dot data equals such and such. Put it in a for loop. You don't return anything. You can say return at the end to say exit the function, or if you just hit this closing curly bracket, the function will return automatically. But you don't say return x or return 0 or something like that, because the void up here says there's nothing being returned from the function. Okay, so that's the function you're developing, is just this function called init, and you need to define this structure in order to be able to talk about a struct node in here. So define that first and then write your init function. And when you're ready to assess it, there's a test bed called main 202.0. You can link with this, right? So compile init.c, link it with main 202.0, make an output file called 202, and then use the assess command. Executable program is main 202, source code is init.c. Use the G command to assess, you should get 10 out of 10. But I recommend before you do all of that, test the code yourself. Write a main program that starts off like this, right? Declare an array of 100 struct nodes, pass it to your init function. Okay, how do we know if we've succeeded or not? Throw in some print statements. Print out data bracket 0 dot valid, make sure it's a 1. Print data bracket 0 dot data, make sure it's a 42. Print data bracket 0 dot next, make sure it's a -1. Now do 99 more sets of print statements and print out data bracket I dot valid dot data dot next and make sure they're equal to what you expect. And if you just print those in a for loop, you'll get 100 lines of output. You can just stare at it and tell really quickly if it's working correctly or not. Yeah?
So just to clarify, the struct node bit that we write, that's not inside any function, it's just one.
You can put it in a function, but don't. Just put it in the beginning of your file.
Okay.
Right? Because you really want it to be available for main and you want it to be available for init.
Yeah.
And ultimately, we're going to throw this in a .h file and include it everywhere, so we don't have to keep typing it. All right? Because if you type it in the wrong order in one file, weird things happen, and it's not obvious. But for now, yeah, just type it in the beginning of your file. All right, any other questions about this? It should be pretty straightforward, but again, it's the unknowns that can end up taking time, right? If you've never declared an array like this and you don't know how to do it, it might take you some effort and some trial and error to figure it out. So play around with that sooner rather than later. Run it through the assessment system, make sure you get 10 out of 10. Okay, and you should be good to go. And if you like type defs, you can use a type def, but I'm not going to talk about type defs yet. So if you don't know about type defs, don't worry about it. Just say struct node when you want to make something a struct node. All right, so I would like to play around with linked lists. I would like you to play around with linked lists. Let's see how many people. So we've got about 20 people in here. So there's plenty of space for 5 groups of people. So I would say let's do 5 groups of about 4 people per group. Find a friend or make new friends and pick a spot on the board. We can have a group over there and 2 on the back, 2 in the front. There should be plenty of markers. Find an eraser. There should be at least 4 erasers around. And what we're going to do is we're going to build up a table like this, right, with an array of these struct nodes containing data next and valid. And the first thing we're going to do is we're going to initialize this. And then I'm going to give you a set of operations to perform on your list, and I want you to go ahead and make these updates. And we'll do the first one together, and then I'll let you do them on your own, and I'll walk around and see how it's going, and so on and so forth. So find some people to work with, pick a spot on the board, and make yourself a table like this. You probably don't need the comments column, but just an array of about 10 entries with data next and valid fields. Something that represents an array of struct nodes. Where we go? All right, so go ahead and make yourself an array of these struct nodes. Probably about 10 entries will be fine. But label your columns data, next, and valid. So just like this part right here. So that.
Index. I got it. Sorry, that wasn't. I wasn't trying to be mean. You just couldn't read. Because you're short. Yeah.
So our ODP goes a little nuts, and it does a whole bunch of initialization, but we don't really need to do all of that initialization from ODB 202. I'm asking you to do that just for practice. But in reality, if we want a linked list stored in a table like this, there's only one thing we really need to initialize.
The 0.
And that's the zeros in the valid bits. So, so go through and mark all of your valid entries 0. Nice throw. And the 0 is telling us when we're looking for an empty spot to use, we can use any spot that has a 0 in the valid field. So we're basically saying that there's nothing in this array that's being used.
And for the 0 index, should it look like this where you declare where your next one is? Or
Yeah, so we'll do that one next.
Oh, okay.
So this is basically saying that all of these cells are available for use, which is important because there's always some value in these memory locations, and they might be zeros, they might be non-zeros, they might be ones, in which case it would look like this was part of our list. So we set all those valid fields to 0. The other thing we need to do is we need to set up the Sentinel node. So the Sentinel node is always index 0. So this is the Sentinel. And remember, the only purpose the Sentinel node serves is to point to the first node in your list. And it does that by putting the index of the first node into the next field. Since our list is initially empty, we don't actually put an index into the next field. We put in that special flag which says there is no node following the Sentinel. So our initial next value is -1. Okay, we're never going to use the data field in the Sentinel node because the Sentinel node is not actually part of the data we're storing in the list. So we don't care what's in the data field. And we know there's always a Sentinel node, so it's up to you whether you want to set the valid bit to a 1 or a 0. If you set it to a 1, it might simplify some of your coding. If you set it to a 0, that's fine as long as you remember that you can't actually use this index 0 entry for data. It's different from all the other nodes. So it's up to you what you decide to do in the valid as long as your code knows what to do. Okay, so that's what the table looks like for an empty linked list. There's nothing stored in our list right now. So let's go ahead and let's insert the number 30. So we're going to make a linked list with a single node which has a 30. And when you're looking for a place to store a node, we're going to use the following algorithm. Start from index 1 and find the first index where valid is 0. So we're always going to start from the top of this array and store in the first spot that's available. All right, so everybody has successfully updated their array. Let's figure out how we did that. So what were the steps that you had to do to insert 30?
Find the next valid bit. Index.
Okay, so find an entry with valid equal to 0. That's a spot where we can store. And so we just visually scan down and we find a 0 in this first spot. What else do we do? How do we do that? Okay, set, let's just insert 30. Set dot data equal to 30, so we'll put a 30 in here. What else? Okay. So set this equal to -1 to say that's the end of the list.
And then change the pseudo.
Set the previous next equal to 1 to point to index 1. So this is a 1. What else?
Set valid to 1.
Good. Set index 1 is valid equal to 1. And I think that's all we need. And those are pretty much the same 5 steps we're going to do every time we want to insert something. Now there's an extra step, which is if we're trying to insert things in order, we're not necessarily going to insert right after the Sentinel node. We might have to look through our list and figure out where to insert it. Okay, but that's a detail for another day. We'll just assume that, you know, we found the right spot to insert this thing. Okay, so let's insert a 40. Cool. All right, perfect. So, so we found the next spot, which was down here, entry 2. We set the data to a 40. We set the next field of that to -1 because there's nothing after it. We found the previous entry, which was a 30, and we changed its next field to point to the 40. In this case, that's a 2. And we set this new entry's valid to a 1. So there's a linked list with 2 things in it. Okay, well, you know what's coming next, right? So insert a 35.
It's a macro aggression. Not really. I would never do that. That's a lie I have several times. Friend group is abusive. It's okay for abusive. Don't go there.
So you said you didn't in your
Yeah. Yeah, we're keeping things in sorted order by data.
Let's see. So we start with 30. 30 looks like it's pointing to 40. Okay, yeah, so we want these things in sorted order.
Oh, they are supposed to.
Yeah, yeah.
Okay.
Perfect. All right, so everybody's got this, but it's a little trickier doing this one, right? Because we're putting something in between 2 nodes. So let's start to think about some pseudocode for doing these insertion operations. So let's think about insert n. Let's call let's find the first open spot in our array, the first spot where valid is 0. I'm going to call that current. Okay, so in this case, current is going to be equal to 3. Right, because that's the first spot that hasn't been used yet. So I'm going to say assuming this array is called data, right? Data bracket current dot data is set equal to n. So I'm going to put my 35 in here. I'll go ahead and set the valid bit while I'm here. Data current dot valid equals 1. So that says this is a piece of data that actually is meaningful to us. All right, we need to find the node that comes right before the one that we're inserting. And we know from looking at it that's going to be node 30. So I'm going to give that a name. I'm just going to call that previous equals index of node prior to the new node. So in this case, previous is equal to 1, right? That's the index of the node 30. Okay, so the adjustments that people made were the following. They wanted to change 30's, this entry's next field to point to our new piece of data. And then they changed this new piece of data to point to a next value of 2. Right, so everybody said 35's next is 2. Where did that 2 come from?
That's the index of the 40.
Right, that's the index of the 40. How do we know that that's what we want the index to be? Because that's what the 30 was pointing to. So the order in which we do this can make things a little easier. In particular, if we set up this next field before we change the previous field, we can avoid having to remember something. So I'm going to do something like this. Data bracket current dot next equals data bracket previous dot next. Does that make sense? What I'm doing is saying, let's look at the previous node, let's look at its next field, let's copy that into the current node's next field. So now our new node is going to point wherever the previous node was pointing. And now we can change the previous node to point to our current node. And that's something like data bracket previous dot next. And what do we set that equal to? Just set it equal to current. Because current is the index of this open spot here. That changes this to a 3. And now I've got the same table that everybody else came up with. But we've also written a little 6-step algorithm that will work for us in general. So let's insert a 10, which is going to go in the beginning of the list. And let's do this by following these steps. So step 1, set current equal to the first open spot. So what should current be equal to? Current should be equal to 4. Okay, next step, set data bracket 4's data field equal to n. In this case, n is equal to 10. So set in element 4's data field equal to 10. So we put a 10 right there. And then set that same element's valid field equal to 1. So now we should look like this, 10 and 1. And then set previous equal to the index of the node prior to the new node. Okay, so this is a little trickier. What's the index of the node that's supposed to come prior to our node 10? It's the Sentinel node. Okay, this is where the Sentinel comes to our rescue. The previous value should actually be index 0. And now we just do these last two steps. Data bracket 4 dot next, that's this field right here, should be equal to data bracket previous dot next. Data 0 dot next, that's this entry right here, that tells us this should be a 1. And then data previous dot next, so previous is 0, so Index 0's next field should be equal to current. Current is equal to 4. So we put a 4 in here. And what the Sentinel has done for us is it said if we're inserting in the very beginning of our list, we don't need to do anything special. We treat it exactly like inserting in the middle or inserting at the end. All right, everybody fairly comfortable up to this point? So let me make a general comment, okay? This list of code that I've written here is worthless. Okay? Do not memorize this. Do not put it on your note sheet for an exam. This is worthless. Okay? What's really valuable in all of this is the way that you were updating this table. This is simply a way to make rigorous and systematic what you've already been doing in your heads to make these updates, to do this insertion. Okay? But this is what you want to understand. How do I want to manipulate this in order to have things, point to the next node from the previous node and so on? If you understand this, you can simply watch what you're doing as you insert a node and write it down. Okay? So this is derivable from understanding how a linked list gets inserted into. Okay? But if you don't know how to insert a linked list and all you know is this code, you're going to have problems. Right? Because it's very hard to sort of reverse engineer from a bunch of code, especially if it's written in C, to reverse engineer from that to the intuition of what's going on. So when you're trying to understand operations on linked lists or any data structure, I always want you to try to understand it in terms of the data structure itself, not in terms of the code. Okay? Let the code be something that you develop from that understanding. And the code you come up with may not look like this. There's different ways you can code this. This is the way that sort of feels natural to me, but it's going to be different for different people, which is another reason why, if you want to come up with this on your own based on how you're thinking of this. But then once you have this, it's very valuable because you can take this and turn it into C. Right? And then when you're debugging, you can come back through here and say what should be happening, and you can use GDB and say, hey, my data current next is equal to 0. That's not what it should be, right? And you can work through here and figure out where the error happened. All right, so let's do a deletion. And we can make a bit of a picture here right now if we want, right? If this is our Sentinel, this is pointing to a 10, which is pointing to a 30, which is pointing to a 35, which is pointing to a 40, which is pointing nowhere because this last node's next field is equal to -1. So let's delete the 30 node. And how does this change your table?
I was thinking of 35.
The previous one next is point here. We want to actually make that point.
Okay, yeah.
So,
Yeah, I get it on here.
oh, the way I'm writing it. Kind of super code, kind of. So previous dot next. I'm getting.
Yeah, he doesn't even have an
so
open name.
you can imagine. We're next.
Did you update your table already?
can't believe he called me.
Yeah, you did.
No way to get
Well, no, I don't think he was. I think he was just trying to guilt trip me into getting drafted.
Sorry, yeah. This guy's point there. We want this guy to not point to there.
Like, imagine going and signing up for that and be like, what did you say? I hurt this guy's feelings and I just felt bad. I hated to make it up to him.
Imagine choosing.
Yeah, this is not. But, right, we want to go over it.
Well, he didn't even stay in the call to let me apologize. He just hung up.
All right, perfect. So we want to delete the 30, right? The whole trick is to take the 10 and have it point to the 35. So it basically skips over the 30. And so we can write a series of steps for that. So we can say something like, current is the index of the node to delete. So we're trying to delete the 30. Well, that's index 1. So current's going to be equal to 1. And again, we need to know what the previous node is, because that's the thing whose pointers we're going to change. So let's have previous be the index of the node prior to current. And we're thinking of this as, when I say prior, I mean prior in the linked list, not necessarily prior in the array. And in this case, the node we're deleting is 30. The node before it is the one with a data value of 10. That's index entry 4. Okay, so previous, I'm setting equal to 4. Once you have those two set up, now it's simple manipulation of fields. So what did people do? They said, let's take the previous node and let's point, instead of pointing at the current node, point where the current node points. Okay, current is equal to 1, that's pointing to 3, so let's change our previous node and have that point to 3. So that's current, data bracket current, dot next equals data bracket previous, dot next. So index 4's next field should be set equal to index 1's next field. That's a 3. Okay, that's removed that node from our linked list now, because if we get to node 10, the node following that is suddenly 35. We've skipped over the 30. The other thing which everybody did was they changed the valid flag on this deleted node. So data bracket current dot valid should be equal to 0. That removes it from the list of valid nodes. So this becomes a 0, and our data's been deleted. The next time we insert something, right, we'll start off by finding the first entry where valid is equal to 0. That's going to be index 1. We're going to reuse the spot the next time we insert something. And if we delete the first entry in a node, right, the previous one will be 0, and we'll set the previous one's yeah, we'll use whatever the previous one was pointing to. We'll set that into the current nodes next. So this will automatically work with deleting the first thing in a list, and it'll work with deleting the last thing in a list. So insertion and deletion, fairly straightforward if you do the right steps, right? It's only a few steps, but if you do them in a different order, or you change something from next to previous or something like that, you can get all kinds of wacky results. Okay, again, come back to pictures. And graphically, here's what our empty list looked like. We said insert 30. We created a new node. We said its data value equal to 30. We changed the Sentinel to point to that, and we said 30 is the end of the list. And then we said insert 40. We created a new node with a value of 40. 30 should point to it, so we changed 30's next to point to 40, and we said 40's next to -1 to say that's the end of a list. And then we said insert 35, so we made another node with a value of 35. And we changed the previous node 30 to point to that, and set 35 to point where 30 had been pointing. And then to insert 10, we made a new node with a 10. We looked at the previous node, which was the Sentinel, and we changed that to point to our new node, and we set our new node to point where the Sentinel had been pointing, which was there. When we implement this in memory, this is how the list is going to look. It's going to be all jumbled up, just like it's all jumbled up in our array, right? First, second, third, fourth. That's okay, right? We're going to be able to follow this in the correct order because we're never just going to move through the array and say, there's a 30 and a 40 and a 35 and a 10. We're never just going to move through memory and read out the locations that are stored in there. We're always going to follow the links, starting with the Sentinel, which in this case is going to say, the first node is a 10, followed by a 30, followed by a 35, followed by a 40, followed by nothing. And then when we deleted the 30, we took the thing that was pointing to 30 and changed it to point where 30 was pointing. So we got rid of this, and we said, let's point over here. It turns out 30 is also pointing to 35. Right? We didn't change 30's next field. But since nothing's pointing to 30, right, it's effectively removed from the list. But if you're debugging this in memory and you start looking through, you might stumble across this node with a 30 that's pointing to 35, that's pointing to a 40. That's okay. Right? Again, we always start from the Sentinel. We just follow the links.
Could you go back to your pseudocode for a second?
Yeah. For insert or delete?
For the delete.
Okay.
Isn't the current dot next and the previous dot next backwards? Shouldn't it be the other way around?
Yeah.
We don't want to change the node we're deleting, right?
It's very possible.
Because the current is the one we're deleting, so we don't care what its next is. We care what previous' next is. So we want the previous next to be the one that's assigned to, correct?
Yeah, I think you're right. Yes, very good. Thank you. Right, so take what the current node that we're deleting is pointing to and have the previous node point to that instead. Absolutely right. And then take the current node and mark it as invalid. All right, questions about this? So what I'd like you to do is double check your understanding of this by doing the following. I'm going to pass around some worksheets. Go ahead and take 2 of those each, and there's 2 copies of the table on here, so if you take 2 sheets, you should end up with 4 of these tables. And I'd like you to do what we just did, starting with an empty list, doing the following operations. So insert a 10, insert a 20, insert a 5, insert a 15, delete a 10, insert a 2, insert a 25, and delete a 2. So we've got 8 operations. You can do 2 of them on each table, and then just copy your table over to the next spot if you want, so that you have enough space to not have to scribble everything out and make it a mess. So that basically I can look at what you've done and see that you are doing these inserts and deletes correctly. I'm not going to grade this, okay, but go ahead and put your name on it and turn that in tomorrow. And I just want to kind of make sure that people are thinking about this the right way. And so we've got 2 minutes left. Let me tell you where we're going from here. This is a very particular way of implementing a linked list, right? We're using an array of struct nodes where a struct node has these fields, and we're using a -1 to represent the end of a list. And we're using integers to represent indexes, and so on and so forth. Okay? That's one way to implement a linked list. There's lots of other ways we can implement linked lists. As a user, as somebody who's writing a program that needs to use a linked list to store data, we may not care about how the linked list is implemented. Right? Typically, we're not going to write linked list code ourselves. We're going to use a package that's supplied to us to implement a linked list, and we're just going to go ahead and use this, right? And we don't care that the person's using a -1 or a -2 or a -99 to say that something is the end of a list, or that element 0 is the sentinel node. We may not even care if there's a sentinel node. So what we want to start thinking about tomorrow is what a linked list looks like from an abstract point of view. If we don't care how the linked list is implemented, what does a linked list look like to us? And it's really just a collection of data with which we can insert, delete, search, and maybe traverse, go through and see what all the numbers are that are stored in there, in a way that always keeps the data in ascending order, right? And we're not going to worry about any of these details as a user. So tomorrow I want to start talking about what a linked list looks like as an abstract data type, and then with that mindset we'll look at PA1 and see how we can implement a package that lets us do things with linked lists using this approach, but in a way where our main program doesn't have to worry about these details. Okay, so that'll be PA1. We'll also talk about the next ODP. Go ahead and write up your sheets at home doing these list operations, and just go ahead and turn those in tomorrow. And if you can staple your 2 sheets together, there's a stapler over there. That would help me keep them straight. All right, any other questions? Cool, I will see you next time then. Yeah, that's why I say next time instead of tomorrow.